Zanya Sofra on the stage. She'll be talking about exosome. Will the newcomer shift the PRP position? So a little bit about Dr. Zanya Sofra. Dr. Zanya is a doctorate in neurophysiology from City University London, doctorate in clinical psychology from New York City, and award-winning international speakers and faculty members in several medical and anti-aging societies. Without further ado, I would like to let Dr. Sofra, let us give a round of applause to her.
Thank you very much. Thank you for inviting me. I appreciate the invitation and I'm grateful. I'm very excited to be here. And I have no conflicts of interest. And actually, let me show you the slide before. I'm going to be talking about PRP versus exosomes, the good, the bad, and the unknown. And I will give you everything, not just the good, but also the bad, everything that you need to know about it. This is a review of about 430 articles that I've been through over the time. And let's talk about what PRP, I'm sure everybody knows what PRP is. It has to do with the purification process. As you can see, this is the PRP. You see a very, very tiny part after the second spin that you can produce. And it has been used very widely in orthopedics, in burns for plastic surgery, in facial rejuvenation. Now, I looked into this review article, had about 18 articles on PRP on cells, 10 on animal research, 16 on clinical studies. The animal research I'm not very fond of because it's very different than clinical research. 24 on skin aging, and about 4 of them were on the limitations of PRP. So most articles out there are going to tell you how wonderful PRP is. And why is it so wonderful? Number one thing that they all say that it does is that it increases collagen. And as soon as we say these days, oh, this increases collagen, we say, okay, we don't need to hear anything else, but you should hear more. Why? Because collagen is out of thousands and thousands, about 400,000 proteins in the human body. And only in the skin, you have 8,987 proteins in the outer epidermis and 9,140 in the inner epidermis. 18,127,000 proteins. Now, youth is the result of the proteostasis, or the homeostasis, we call it proteostasis, of all these proteins, not just the presence of collagen. And that's something that you need to understand. So collagen is one of over 100,000 proteins that have been identified. It's about 400,000 now that are unknown. So rejuvenation is the result of the protein homeostasis. Just one protein being very much is going to create keloids, like, collagen. Too much collagen will create a keloid. So it's not merely the lack of collagen. So that's a very important thing to kind of keep in mind. Now, the PubMed has reached and searched research articles on the adverse effects of PRP. And there is quite a few adverse effects that come from PRP, especially with people that use it purely for rejuvenation and it's not for orthopedic or other usage where it has been very successful. So the most commonly reported adverse effect is infection. And why is infection? And of course, let me go back. Why is the infection? Because the PRP cannot be, basically, the pharmaceuticals cannot be clearly purified as well as pharmaceuticals are purified. And that's why you could have an infection because of PRP that has not been completely purified. So you have to be very careful. And a lot of side effects include blindness, inflammation, allergic reactions. So if you go for rejuvenation and you end up being blind, that's not a good thing. So let's talk about exosomes now, because we need to compare the two. And the exosomes have been used for scar removal, for skin rejuvenation, for hair growth. There is a lot of exosomes for hair growth, and of course for pigmentation regulation. And exosomes come from a number of sources. They come from saliva, from breast milk, blood. Basically, the exosomes are communication agents within the body. And the fathers of this wonderful newcomer is these three scientists, Rothman, Shackman, and Sudhoff, that got the Nobel Prize in 2013. I've been following their research since the year 2000, and it was very exciting when I heard that they actually got the Nobel Prize. The exosomes, they're tiny. They're like about, at the most, they're about 100 nanometers. Which means nanometers is you cannot, obviously you cannot see it with naked eye, it's impossible. So they originate and they're released from the exocytes. And you can see here, you see that's the endocytic vesicle, and then you have the multivesicular body, and you know the liposome, they originate from the endosomal network, and from there you have the exosomes that basically this is a cell. And they are for cellular signaling. They are what signals within the cell, within the body. And they are responsive for, they play a big role in the immune defense. That can be a double-edged sword, because if they give the wrong signal, then the immunity can be affected very dramatically. And of course, they have a very important role in genetic material. That's again kind of, it can be a tricky thing. So exosomes are made of intraluminal vesicles, and as you can see here, that's the multivesicular bodies and the liposome, and then you have the exosomes. That's under the microscope to give you a more scientific look at this. And they contain a lot of things. So this is an exosome, basically. What you hear, signaling proteins, cytoskeletal proteins, metabolites, nucleic acids. This is the exosome, just so to show you. They're really like packages that you send with FedEx or DHL to reach from one place to another place. So the exosomes carry all this information from one cell to another. And they are basically divided, they can be divided in two ways. In the necessary endosome sorting complex, or they can be independent. They can be dependent on it or independent on it. And independent on it, they have to be connected to lipids and essential proteins. This is molecular biology, but I'm putting it in as an information for you. They are the primary components of cellular communications, which is what I was so excited, because this was my interest, cellular communications and signaling. And basically what you can see, they can fuse with the membrane and deliver the information, or they can be part of the sort of taken in through endocytosis and to deliver the information. This is the method of how they deliver. Now, they are a cocktail of long non-coding DNAs. They are microRNAs, messenger carries, messenger RNAs, which again, that's molecular biology, and I'm putting as more information for you so you can understand what they are, what exosomes are. They have proteins, they have small RNAs. Again, that's another slide that has to give you more kind of information about what's inside each exosome. And again, that's another cell communication by extracellular vesicle RNAs. RNAs transfer information from the DNA to the cytoplasm, from the nucleus to the cytoplasm, and that's how proteins are made. And proteins are the brains of the cells. So it's important to understand what's inside in an exosome before you try to inject it. So what is the problem with exosomes? Number one problem is purification. Why? Because they have contaminants inside them. Okay, so when they're not purified, then there becomes a problem because the contamination inside it creates nonsense signal, it creates nonsense proteins. It carries proteins that are not giving the correct signal. If the correct signal is not transferred properly, the other cell, the whole system is going to become chaotic and it's going to be a huge problem. And this is the different purification methods, and you can see the at 99%, the functional ability of the exosome is lost. At 50%, you could have damage because it's only 50%. So we're still in a process of trying to figure out how we can purify them, but maintain the number of exosomes that you want, so we don't lose the quantity by improving the quality. And this is what's happening right now. You increase quality, you lose quantity, you increase quantity, you lose quality. So the other problem, he said there's a problem that everything in the body has exosomes, and where you got it, a cell can have a lot of exosomes in it. And if you give into the injection the wrong number of exosomes, then you could have a worse problem from that you had before. The main problem with exosomes is that they are used by viruses and also cancers to kind of transfer the wrong information, the bad information, and that is the dark side of exosomes. So they have contributed in the development of many diseases from our investigation. The other thing is that they're wonderful for cancer. You have some research that says, yes, use it for cancer, and there is some other research that says no, do not use for cancer because they create more cancer. They kind of get metastasis far more to prolong the process of cancer, and also they create more metastasis. Now, exosomes have contributed in the development of several diseases, but at the same time, they have very powerful therapeutic effects. So it's a scale here. Should I use them or should I not use them? And the pathogenetic effects depend on how inflamed the person is. So if the person has a lot of inflammation in their system because they're very old or because at the doorstep of some illness, then the exosomes might have a pathogenic effect on them. If they're very healthy, then they're going to have therapeutic effect. So the pathogenesis of the person is very important. You need to know if your patient has a very high level of inflammation. And CRP, for example, if their CRP is very high, it might not be a good thing to do exosomes there. So exosomes have been observed to also transfer misfolded proteins. What is a misfolded protein? Is a protein that is non-functional. A misfolded protein gives nonsense signals. If I give nonsense signals to a cell that it divides, then that cell will become a cancer cell because it doesn't have all the instructions that are necessary for it to divide. Whoops. Okay, that doesn't work anymore. Okay, so now tumors also communicate through exosomes, and that's another thing you need to remember. So tumors will also have been observed to be involved in the spreading of pathological misfolded proteins, and that is going to go into the system. Now, at the age after 50 or 55, we all have cancer cells. It's just our immune system is dealing with it, but if information starts expanding and being transferred, then it can become a problem. So the beneficial effects are 50-50. Some of them are very beneficial and they're necessary for certain disorders, especially when there is no other choice. And at the same time, you have cancers and virus and neurodegeneration that can also be transferred with stem cells. Now, with exosomes, sorry. So the exosomes carry the RNAs, okay? These are involved in genes, in how the genetic expression happens. And we express genes for different reasons. When we're happy, when we're sad, because there is time to be expressed, because somebody hit our head with something, or whatever. So we express in genes. So gene expression is not always a good thing. So reinforcing gene expression does not mean that this is going to be a good thing. Some genes have positive effects and some genes have negative effects. For example, I don't know if you're old enough to know about the craziness about telomeres, and they had the telomerase and creams and injections and all kinds of things. Well, as it turns out, a mutation to the POD1 gene gives basically these people, their telomeres never get shortened. Telomeres get shortened normally when you're aging. Okay, they get, when it divides, it gets shorter. But these people do not get shorter telomeres, so they should be healthier, right? And they should be more rejuvenated. No, it's the opposite. Actually, they had cancers. 15 out of 17 people had both malignant and other tumors because of this inability to shorten their telomeres. So another very important thing about gene expression, as you can see here in the liver, do you see this is the ages? Do you see the reversal on the blue in all of them? So what is good for somebody who is young is deleterious for somebody that is old. The exact same process. So age, when you look at exosomes, is extremely important. So applications, challenges, and prospects, they are very good for several diseases. However, the purification process is very important, and that's something you need to look at. There is concerns and challenges related to application of exosomes in regenerative medicine. And I'm just talking about anti-aging medicine and regenerative medicine. So although exosomes therapy may serve as a new approach to combat aging, and it's very promising, but at the same time, we need a lot more research, and we need longitudinal research, because we need to know if there is a greater incidence of a certain disease as a result of applying the exosomes. So can exosomes replace PRP? Both procedures have advantages, but both procedures have adverse effects. So you need to kind of balance it out and see. Now, there's new technologies, and I would like to introduce you to these new technologies that are developed, started in about 2020, and it has to do with resonance transfer, and I'll show you what that is. Hold on, let me see if I can play the video. Yeah, you see? This is resonance. One cell transfers the energy and through resonance. It's a fascinating new technology. It started in the 50s, but they did not, it's only now that they start using it. And basically what it does is through resonance, it helps proteins to be folded again. Remember, a misfolded protein is useless. It's gonna create a problem in the system. And a folded protein is gonna be the brain of the cell. So it's a press release from another Nobel Prize that how the cells can kind of, if they kind of have the proteins folded again, and that's what this resonance new science is about folding proteins, and they have also a coefficient that they use. So when you boil an egg, for example, a boiled egg has its proteins unfolded, and it cannot go back, okay? But if you could potentially fold on these unfolded proteins, then you would have what we call we can kind of unboil an egg or unfry an egg potentially. But that is major because they can help with several illnesses and several and cancers, and this is basically what this article is, that signaling molecules that associated with the protein folding. So what is basically what it does, you see this is a folded protein, and with heat or environmental toxicity or whatever, it gets unfolded. And then it gets renatured through this process of resonance. It becomes functional again. So basically, you bring it back from the dead, and you can do that at the molecular level. You cannot do that with whole objects because they become a crystal. And this is basically what you look at, under the microscope, and how signaling resonance energy transfer restores protein function and protein folding. And with this, I would like to thank you for your kind attention. Any questions, Stacy can answer later.
Thank you very much, Dr. Zania. Very informative, very information. I guess, when I look at the topic today, from early in the morning until now, we are talking about hair technologies, hair new advancement. I guess in another 5 or 6 years' time, you won't be seeing people balding.